Hi, everybody. I'm going to talk to you about Chapter 3 quantities, which are vectors, basically. So, we've talked about vectors before. This will be an entire chapter on vectors. So we did this before, right? A scalar is something that you can specify with one value. So it could be temperature, it could be mass, could be the speed that an object's moving at. Whereas a vector quantity, you have two numbers that you need to specify, which we usually say is a magnitude, right? So have kind of a quantity and then also a direction. So for example, velocity is vector, right? You might be moving 10 meters per second in the positive x-axis, or acceleration is minus 9.8 or 9.8 in the negative y direction, meters per second squared. Okay, so we didn't really get into univectors when we talked about vectors last time. So these are vectors that have a length of 1, and we just use them to indicate the different directions. So oops, sorry about that, didn't know that happened. So the I hat vector is pointing in the x direction, the j hat vector points in the y direction, and then there's also a k hat vector that points in the z direction. So again, these are telling us direction. They just have a length of 1, so they don't change the quantity when we multiply something by these vectors. Okay, so a vector, in a simplest sense, we can think of really as just an arrow, right? So we see here the vector A, it's starting at the origin and pointing up to the right along some distance, right, and at some angle. So we will often go back and forth between representing a vector as this arrow pointing at some direction, and also its components, which you can think of as the sides of the triangle, right? So it has this component in the x direction, and then also one in the y direction that would look like that arrow, right? And vectors you can kind of slide around in space. We can put that y arrow there. It doesn't actually change anything about the vector A. So we call ax and ay the components of the vectors. So for the notation here in the slides, bold is indicating vectors, and then the italics here are just the scalars. So that would just be the length of this component vector ax, right, or the length of ay. And those are scalar quantities. Okay, so we can use Pythagorean theorem to relate the length of ax and ay to the length of the total vector, right? That's just a squared plus b squared equals c squared. That's what we have written here. And then we can also connect to the angle theta using trig, right? So tangent would be our opposite side, which would be the y side over the x side. And then we would take the inverse tan of both sides to get theta by itself. So we could write theta as the inverse tan of ay over ax. And we'll get some practice doing that in a minute. And then we can also go from the length A and the angle to figure out what the components are using trig as well, right? So this is, ax is the adjacent side of theta, so cosine is our adjacent over the hypotenuse. And if we solve for ax, we get that it's the length of the vector A times cosine theta. And then we can do a similar trig operation to get us the y side using sine, right? Because sine is the opposite side over the hypotenuse, so that would be sine theta is ay over a. And if we solve for ay, we get it's a times sine theta. Okay, so there's lots of different ways that we can represent vectors in terms of their components. So sometimes you see, so let's say we have one vector p, again, it's just some arrow, right? So we could say that it is the x, y, and z components. Sometimes you see it as x hat, y hat, and z hat. So that's one way of representing those unit vectors, right? So it's got this much pointing in the x direction, this much pointing in the y, and this much pointing in the z direction. We just talked about the I hat, j hat, and k hat as well, right? So you would write the vector out as its component in the x direction times I hat, component in the y direction times j hat, component in the z direction times k hat. A column vector is something you're not going to see in the book, but we'll use periodically in class because it's a really nice compact way of representing the vector. And for those of you who've done some programming, it's almost like you're putting it in an array, right? Or so the vector p we could write just as we put it in this long brackets and just put the x component on the top, y and z on the bottom. And sometimes when we're just doing two-dimensional motion, most of what we're doing is two-dimensional, we just have the x and y and kind of leave out the z. But this is a totally equivalent way of representing the vectors, right? Any of those are good. Okay. So as I mentioned before, we can talk about the components of a vector in a different direction, or we can just say it has a certain length in and an angle associated with it, right? So the magnitude of the vector is the length of the arrow that we're talking about. And again, Pythagorean theorem, we could expand to 3 dimensions. It's the square root of the square of the x, y, and z components added together. The magnitude of the vector can have units, right? So if it's, again, like velocity we talked about, the magnitude would have meters per second attached to it. And magnitude is always positive, right? So the direction is where we might end up getting a negative sign. Okay, so and then if we wanted to determine, again, if we had components of the vector and we wanted to determine the angle, we would use our geometry and trig to do that. So again, just to kind of review here, sine, right, or maybe we'll go back to SOHCAHTOA for those who haven't done this in a while. So sine is our opposite over hypotenuse in a right triangle. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So again, we can just use these relationships. So here's theta, right? This is my adjacent side is x, the opposite side is y, and the hypotenuse would be r in this case. And so if it's been a while, just go through and review that, right? So that the sine theta is your opposite over hypotenuse, so that'd be y over r, the magnitude of the vector. Cosine is your adjacent, the x over the magnitude, and tangent would be y over x. So converting between magnitude and direction and the components of vectors is like converting between Cartesian and polar coordinates. So r is hypotenuse and theta is the angle, so that's like our magnitude and direction. And so we can go back and forth between x and y versus r and theta. Right, so the x and y would be the components of the vectors, r and theta are the magnitude and direction. And just note that the theta we will always measure from the positive x-axis. We'll measure counterclockwise this way, okay? So this is like a positive theta, maybe 30 degrees, something like that. Okay, so let's do our first example here. So we're going to start with a vector A, and it is making an angle of 130 degrees with a plus x-axis. Okay, and it has a length of 5. Just sketching it on my notebook here, and then we'll go over to the camera. And we need to find AX and AY. Okay, so let's go to our ladybug camera. All right, so this is what we have, right? That's our angle, 130 degrees. And so I usually like to just try and visualize this as like kind of a regular triangle without this big, is it an obtuse angle? I should know that. Okay, but I'm going to try and draw my triangle like this. So that's one side of the triangle here, and that's one there, right? So that would be my AX, and this is my AY. So I know this is 130 degrees, and I know all the way over to this angle is 180 degrees. So that means in here, I call that theta. Theta is going to be 180 degrees minus 130 degrees, so theta is 50 degrees. Okay, and now I can use this triangle to solve for my components. So if I look at my trig functions, right, so just kind of let's sketch that triangle out over here again. So here's my vector A, this is AX, and this is AY. And that's theta. Okay, so if I do my trig functions, right, so here's theta, my adjacent side is over here, that's AX, and my hypotenuse is A. So I'm going to start with cosine, and just write this out until you get that hang of it. So it's my adjacent side over the hypotenuse. In this triangle, it's AX over A. And we're solving for AX, right? That's one of the things we need to find. And this is what we're given out here. Okay, so I want to solve for my unknown. So if I multiply both sides by A, I get AX is A cos theta. Okay, and we can do the same thing for the y component using sine. So again, write it out till you're comfortable with it. Sine theta is my opposite over hypotenuse. opposite side over the hypotenuse. In this triangle, opposite is AY, my hypotenuse is A. And then again, that's what I'm solving for, AY. So AY equals A sine theta. Okay. All right, so now we are ready to plug in, right? So AX is A, which is a length of 5. We don't have any units on this. And then I have cosine of 50 degrees. And AY would be 5 times sine of 50 degrees. So let's go over to my Python window. And I kind of import this in a cheater way. So let me go back and do this. So if I want to solve for AX, it's 5 times NumPy has a cosine function. And then NumPy always wants to take radians. It's just like in your calculator, you got to think about what you're feeding into the cosine function. So I'm going to convert my angle to radians. And then we can just print out what AX is. So I'll write that down here. AX is 3.2 meters. And we said for significant figures, we'll stick with 3, right? So actually I'll do 3.21. Okay, and then for AY, it's the same kind of thing, AY, except now instead of sine, I have to do instead of cosine, I have to do sine. Again, we'll print that out, and I get AY is 3.83. Oh, I put meters on here, but the problem actually didn't even have meters. I just made that up. Okay, so let's see if instead, so I broke this up to show, to write things in terms of this angle theta, but what if instead we used this 130 degree angle? So let's see what we get for AX if I use 130 degrees. So it tells me actually that AX is in the negative direction, so which I should put in at the end as well. But and let's see what AY comes out as if we do 130. Okay, so AY comes out as the same, 3.83. So if I am defining my coordinate axis, right, I said that this is my plus x, and I know actually just by drawing that that is in the negative direction. So when I solve for my trig, I then have to remember to say that AX is in the negative direction. So it's negative 3.21 I hat, and AY is in the positive y direction, so 3.83 j hat. Okay. If you use the angle as defined from the plus x-axis to your vector, that negative sign comes out automatically. My preference is to draw like a regular kind of triangle and then just, think about what direction these components are pointing in. Okay, so AX in this case is negative 3.21 I hat, and this is 3.83 j hat. Okay, so notice when we add these up, they don't add to 5, right? Because we're getting like sides of a triangle, that it's not the same as just adding numbers, right? We're adding vectors. Okay, okay, so now we're going to do an opposite problem, which is if I have the components of the vector, how do I get the magnitude and direction? So let's write this one out. So we have the vector B is negative 2 I hat plus 2 j hat. And we want to find the magnitude and direction. Okay, so we have the vector written out there. I'm just going to sketch what this looks like. So it's saying that I have a component so again, here's my plus x. Should be pretty deliberate about this to start out with, plus y. 1, 2, 3, 1, 2, 3. Not exactly the same scale, but you get the idea. All right, so it's saying I have a component in the negative x direction. So I'll do that in black. So I'm going minus 2. My x component looks like that. Minus 2. And then my y component is up 2, so 1, 2. Okay, so my vector then starts from wherever the origin is and points to the end of my y component when I do my tip to tail addition. So let's just write that over here, right? So I have minus 2 in my x component, so I can make them a little bit better matched in length. 2 in my y component, and tip to tail addition, remember you go from the start of the original vector to the end of the final one. So that's what A looks like. Okay, that's my vector A. All right, so we want to find our magnitude. And so remember, this negative just tells us that we're pointing left. The actual length of this is 2. So the magnitude of A, which we write like that, right, inside these vertical lines, it's an absolute value kind of. So this is going to be ax squared plus ay squared. All right, when we square this, the negatives go away, right? So we have negative 2 squared plus 2 squared. So we get the square root of 4 plus 4, square root of 8 is 2 squared of 2, right? So that's the magnitude. We can get an actual number for that if it makes you feel better. All right, and then we want theta. So again, I would draw my theta in here as my triangle, right? And I know the tangent of theta. So tangent theta is my opposite over hypotenuse, and that's going to be my y component over my x component. So that's going to be 2 over 2. I'm just using the magnitude here because I already have drawn kind of the direction that x is going in. So then if I solve for theta by itself, I take the inverse tan of both sides. So the inverse tan of tan theta, and then the inverse tan of 2 over 2, which is just 1. All right, so inverse tan of tan gives me theta by itself, and then I have the inverse tan of 1, which you might remember is 45 degrees. Okay. All right, so now again, we have to think about how we define vectors, by convention, right? So the angle I solved for was in here, but so we can either say that we have my vector A has a magnitude of 2 square root of 2, and it's making an angle of 45 degrees clockwise from the negative x-axis, actually, right? Because I'm talking about this way. So that's one way to specify it. Or we could say that my vector A has a magnitude of 2 square root of 2, and it has an angle of, if this is 45 degrees, this angle from the plus x-axis here will be 90 degrees, and then this angle in here is 45, right? Because 45 and 45 make 90. So 90 plus 45, it's 135. So we could also say that my vector A has a length of 2 squared root of 2, and that angle is 135 degrees counterclockwise from the plus x-axis. Okay. All right, so we can add vectors graphically. We've done this a little bit of doing our tip to tail addition, right? So we would start with a vector A, for example, if we were doing A plus B here. We draw A, we can slide B around as long as we keep its length and direction the same, but we slide it around so that the tail of B hits the tip of A. And then the sum of them goes from where we started with A to the end of B. And we can do this with lots of different vectors, right? We can do A plus B plus C. Again, it starts from wherever A started to where D ended, okay? So you can always do this graphically. And again, just to show some of these examples, right? So here's another A plus B, and then that's the sum of those. If you are subtracting, remember, so negative B is just flipping over B in its direction. And so if we wanted to do A minus B, we would draw the vector A, we would put negative b, right? Where a ends, you start negative b, and then again from the start of a to the end of b is a minus b. And then if you're multiplying a vector by some constant, you just keep the direction the same and scale the length by whatever that constant c is. Okay, so let's do this problem. So we'll just do one of these. So let's say we have a, we'll do that first set where a is up to the right and b is just not quite as high an angle and a little bit shorter. Okay, and so we want to do what is a plus b and a minus b. So let's see what that would look like. Okay, so let's do a plus b first. Go back to the other pen, it's a little easier to see, I think. All right, so we would just redraw a, so I try and keep it the same length and in the same direction as best as you can. Okay, and then where this ends, we want to take b, the vector b, and kind of slide it down over there. So I'm going that. Okay, and then so a plus b will go from the start of a to the end of b. Okay, and now if we do a minus b, we do the same thing, we draw a again. Okay, and then minus b, remember, will be the opposite of this, right? So it's the same length, but pointing in, they should be like parallel, but pointing in the opposite direction. So that's minus b. So now again, I take that and slide it down. Imagine sliding it down over here. Minus b would be looking like that, or thereabouts. Hopefully good enough to get the idea. Okay, and then so a minus b goes from the start of a to the end of b. Yeah, we should draw kind of as a thicker vector there. So this would be a minus b. Okay, so we'll get some more practice with that in class. Okay, and then if you want to multiply a vector by 2 or a half, basically you're just going to keep the direction the same and change the length. So again, let's take a look at that. So if I had another vector, let's say a. Okay, so if I wanted to do 2a, I would think about my vector a, so I can redraw that over here. And then I'm going to actually expand it, double its length, but keep the direction the same. Okay, so this would be the vector 2a. All right, and then if we do 1/2 a, we're going to take the vector again and think about keeping the direction the same, but shrinking it in half. So 1/2 a would maybe look something like that. Same direction, but half as long. Okay, so we can add vectors graphically, right? We can do tip to tail and figure out what the resultant vector is. If we start doing a lot of vectors, that ends up being cumbersome, and then if you had multiple vectors adding together, keeping track of the angles is a little tricky too. So really, in practice, what we'll be doing is adding them in terms of their components. So if you look at vector A, right, it has its length in the x direction here and its length in the y direction there. And then the vector B has its x component and its y component as well. So when we write these vectors out, we can write A as its x component times I hat, its y component times j hat. Same thing for B, it's x component times I hat, it's y component times j hat. And then we group those terms, right? So here's ax plus bx in the I hat direction, ay plus by in the y or j hat direction, right? And it kind of makes sense. So if you look at R, right, the x component of R is the x component of A plus the x component of B, and the y component of R is the y component of A and the y component of B, right? So that's the x components, right? So we get that. And then again, we can find out the length and the direction by doing the square root of rx squared plus ry squared, and then do our trig function to figure out theta by doing the inverse tan of ry over rx. Okay, so let's do another example here. So we have two vectors that we're going to sum using unit vectors. So we have A is 4 meters in the I hat direction and 3 meters in the j hat direction. And then B is minus 13 meters in the I hat direction and 7 meters in j hat. So what's the magnitude and direction of A plus B? So, all right, so part A, we want to find A plus B in components. And then part B, we want to find magnitude and direction. Okay, so there we go. All right, so we can do find A plus B in 2 ways, right? We can combine basically here, our x components and our y components, right? If we think about what those look like. So here, right, so A plus B has 4 minus 13 meters in the I hat direction and 3 plus 7 meters in the j hat direction. So that is -9 meters in the I hat and 10 meters in the j hat. Okay, and we can sketch those out to see what those two vectors look like as well, which I recommend, but I'm going to just skip here just to keep our video a little bit shorter. And I'm actually going to keep going here because I want to show you what this looks like in column vector notation. So in column vector notation, A would look like this, 4.0 and 3.0, right? And we have the meters in there. I'm just going to drop that for a second. And B equals minus 13 in the top row and 7 in the bottom row. So if we wanted to do our sum using unit vector notation, we would have A, 4.0, 3.0, plus B, which is minus 13 and 7. And then when we sum, we just sum across this row and across that row. So we would get on the top, again, our 4 minus 13 is minus 9, and then 3 plus 7 is 10. So A plus B, we could write equivalently like this if we want to use column vector notation. And when I do it, I think this is just a lot more compact than trying to keep track of all my I's and J's. But you can try it both ways and see which one you like better. Okay, so if we want to find the magnitude and direction, let's sketch out what this vector looks like. So again, we can kind of just put our coordinate axis here. So it's saying that I have a component that is 9 in the negative x direction. So it's pointing to the left. And then I'm going even a little bit higher with a length of 10 in my y direction. So again, I'm going to figure out this angle first, and then we can redefine it in terms of this, and call it theta 2 if we want, which is relative to the plus x-axis. Okay, so the magnitude of A plus B, again, which we write inside the absolute value, right, is my square root of the components. So 9 squared is 10 squared is the square root of 181. I don't know off the top of my head, so let's go to Python. Root of 181. A little bigger. Okay, so the length of it is 13.5. I've been a little sloppy. That should be meters. I've been a little sloppy with my units. You can deduct a few points from my solution. Okay, and then for theta, again, if we look at this triangle, the tan theta, our opposite over adjacent side, is 10 over 9. And so theta, I want to do the arctan of both sides, 10 over 9. So go back here. So arctan of 10 over 9 gives me that, but that's an answer in radians, so I want to convert that to degrees. Degrees, and I get 48, which makes sense, right? Because they're almost the same side. If they were exactly the same size, it would be 45 degrees. Okay, So again, I've defined this angle in here, and convention says that we should really define it relative to the plus x-axis. So theta 2 would be 180 minus this. So 180 minus that, it's 131. Let's call it 132. Around that. Okay, so then to my a plus b, if we want to specify that as a magnitude and direction, it's 13.5 meters, and theta is 132 degrees counterclockwise from the plus x. For the most part, if you're using this convention, we won't have to write that out, but if you're using some other convention, like relative to the negative x-axis, like clockwise from that, you want to write that out explicitly. Okay.